Welcome to the class, students. In the today's class, we'll be dealing with the measurements of the physical quantities. Here we'll try to see how the measurements that are being made, how much precise they are, what is the accuracy of the measurements, and how they are being used by the scientific community for further calculations. So let's begin the class. Let's move to the next subtopic, measurement. In the measurement, we all know it all starts with the ruler. We have been used to measuring the lengths along with the ruler in our classes, primary classes, where we have used the rulers, and we know that normally a standard ruler, small ruler it's like 15 centimeter, and then there are 15 large lines, and then there are smaller lines in between them. Now these large lines, they denote a centimeter, and these smaller lines are actually a millimeter. Now the measurements that we have been doing, what we do is that we place our tip of the scale at a particular end from where we have to measure, and then we measure it by reading along the ruler. What is the length of the ruler is measured by the markings that are shown on the ruler. Now while we are making the measurements, we have measurements of, like in the physics we will be doing measurements of earth, we will be doing measurements of sun, we will be doing measurements of electrons, we will be doing measurements of a normal man or woman. So we will be dealing with all types of bodies, either large bodies, huge bodies like earth and sun, and the subatomic particles like electrons, or the normally that we see in our daily life, in our physical environment, the man and women and blocks and trolleys, things like that. Now what happens is that when the mass is very large, now to represent it in a very compact and precise manner, because it's not possible to write like the radius of the earth is 64 this kilometer, and if you have to write in the standard units of meter, you again multiply with this, and now this is the radius of the earth. So it's not even comfortable to write in this manner. So what we have done is we have found out thing that is called prefixes. Now if you see in the name, there is a word called pre and then the fix. Actually these are the words that are prior to. Pre means before they are fixed with the word, and it helps us in measuring the order of measurement. What do you mean by order of measurement? Now we know that 1000 gram is equal to 1 kg. So if you have to, or you can write it like this also, 10 to the power 3 gram. So this 10 to the power 3 is, we represent not in numerical terms. We will now start using the units that you have used. Is for unit for this was kilo. That is, if you write kg, you actually mean this many grams. Gram is in the terms of grams. So if you have something like 1000, or suppose this many kgs is a mass of something. So now if you have to write it more precisely, you may write it like 10 to the power 5 kg, or suppose you have some name for this, then you can straight away write, suppose x kg something, if x is the name for this prefix. So there are many prefixes that have been put up by the scientist, and they are like this. You know, kilo, you have heard of it, this is 10 to the power 3. If it is kilometer, it becomes 1000 meter. If it's kg, it becomes 1000 kg. Now you have also heard of mega. Mega is 10 to the power 6. Now if you will see one interesting pattern in this is that above the kilo you will find all of the prefixes that have been defined are actually the multiples of 3, 6, 9, 12, and it goes above this up to 15, 18, things like that, up to 21 it goes, and they are all in the multiples of 3. Now for 3 we know this, the kilo is there, then we have mega for this, giga for this, tera for this. This is how the orders have been defined. Now then if we go below for the subatomic particles, when we go to smaller sizes, now we know what these deci, centi and milli are. We have done this. We know milli is 10 to the power minus 3. So again below minus 3 they are again multiples of 6, 9, 12. This we have done. This we know, this up to this we have done in our lower classes. So we know all this. For this, milli is for 10 to the power minus 3, micro minus 6, nano, pico, then it goes like this. This is femto, then there is atto, and this will go like this, minus 15, 10 to the minus 16. There are a whole list, a long list for it. You don't have to go to that level. Well, you can manage it by remembering up to this. Like here you have for tera. Similarly, we have in the below we have up to pico. If you remember, that will be fine. That will do for you for the class 11th and 12th. Now, the limits of measurement. We have been measuring like we are measuring from taking the mass of the body, like in a balance, measuring balance that you have seen, and then we measure with the help of rulers. So we have done various kinds of measurements in our daily life. Now if you see the digital weighing machines, if you have seen it, the digital weigh machines, they show your weight and something like, suppose 62.2 kg, they show weight something like this. So now we know, if suppose something gives you your weight as 62.24 kg, we know that actually this value is actually more precise. It is to a higher accuracy. That's how we use the word accuracy and precision. So we don't have a very clear definition in the literal words when we talk about accuracy and precision. But when we are studying in physics, they are two entirely different things. And these two are the characteristics of any measurement that we make, whether it is accurate, whether it is precise, and what these are, how they are different from each other, that we'll see here. Now, a measure of how close a measurement is to the true value of the quantity being measured is called the accuracy. Means, suppose there is a block, you put it on a measuring balance. This is the measuring balance, and I am assuming that this balance is a very standard balance. It measures the correct value. Suppose this gives me that this mass is 5 kg. Now what I do is that I take this mass, then I have a very local balance, and then I weigh this. Now, how accurate this measurement is to this standard measurement? This is the value that is very standard, that is the correct value. So how close this value is to the value that I get. So suppose if I get 4.2 kg when I measure from this balance, and for another balance, I have balance 2, I get 4.8 kg. So what I say is that this 4.8 kg is more accurate. This balance is more accurate, means this 4.8 kg, this value, second measurement, is more accurate than first measurement. It is how close is to the true value. What is the true value of the quantity? So normally when we have to specify the true value, we can compare from the international system of units, you can measure from there and get to the true values, and then these are the local values, the instruments like that we use in our lab. They are not always very precise or accurate. They are like there are some distortion, someone twisted it, or in the summer it had some expansion, things like that. So it won't give you a correct value. So how this value changes? Now the value that you got it, you can compare and tell how accurate the value are. The closer it is, the more accurate the value is. So if you have something as 4.9 kg, then definitely this is more accurate than this. Now we'll see. Now if we have to look in terms of the figure that I have here, accuracy means how correctly you hit the bullseye. That is accurate. This is where you have to hit. This is the correct point that you have to hit. If you hit it exactly here, that means you are being very accurate. If someone hits it here, he is not being that accurate. Someone hits it, he is even lesser accurate than this and far lesser than this. He is being more accurate. So someone hits in between, he is accurate than these two. So how close you are to this value is what gives us the accuracy. Now we will see an example. The question being asked is, who is more accurate when measuring a book that has a true length of 17 centimeter? It has been given that the true length, this is given, it is 17 centimeter. It has been measured from a standard ruler and given to you. Now Suzanne, what he does is he measures the book and he gets at one time he gets 17 centimeter, maybe he is using different scales. He gets 17 centimeter, 16, 18 and 15. And then Amy, he gets 15.5, 15, 15.2 and 15.3. These are the 4 values that these 2 people get while they are measuring the same book. Now, who is being more accurate? As we said, accurate is being close to the value, true value. Value 17, as we can see from here, the 17, 16, 18 and then 1 is 15. So, in 3 of the times, he is being more accurate, like this is minus 1 below, this is plus 1 above and this is like minus 2. Now, if you see here, you can see that this is minus 1.5, minus 2, minus 1.8, then this is minus 1.7. These are all far below than this. So, this measurement that has been done by Susan are more accurate. Now, what is precision? The precision means a measurement of how close a series of measurements are. This is important here. How close are the series of measurements? Like you are measuring the values again and again and again. The values that are getting there, how close are these values? They have got nothing to do with the true value. As we saw here, suppose this is the true value. We have some true value. I am not bothered about if every time you are getting a very close values, and I am not bothered here how close it is to the true value. If something is very close to the true value, I call that it has a very high accuracy. Now, this is what I call precision, where the series of measurements are to one another, how close they are is what the precision is. Now, a measurement of this accuracy of being the consistent measurements means you are measuring the values consistently, doesn't matter how close you are to the true value, that is precision. So, that means this is where someone hit the bullet, he has hit the arrow, now he has hit this arrow. So, suppose someone else again hits at some path, but he is not hitting the bullseye. But if he is being very all the hittings are being very close, very closely away. So, if I denote this as bullseye, I hit here, here. I am hitting very closers, very close, but not at the bullseye. I have a very high precision, but I am not accurate. Who will be accurate? Who will hit here? He is being more accurate. Now, the same question, who is being more precise in this measurement of the 17 centimeter book? Now, Susan, he gets 17, 16, 18, 15. Now, his values, if you can see, this is 1 centimeter variable, then this is 2 centimeter varying, this is 3 centimeter varying. If you see here, this is 0.5 centimeter variance, this is 0.2 centimeter, and then this is 0.1 centimeter. Obviously, these values are not close to 17, but we can see here that these values are very much close to each other. That means the series of measurements are very close. That's what I call precision. The measurements made by Amy are more precise rather than Susan, because Susan is measuring the values close to 17 centimeter, but at one time it's 17, other time it's 16, then it's 18, then it's 15. So these values are varying largely between them, between the measurements there is a very large variation, 1, 2, 3. So this is not precise. Well, this is more accurate then. Now you can see this from the example, this figure, as you can see, this is accurate or precise. This is neither accurate nor precise. If you see here, this is neither accurate nor precise. This is not accurate, this is not hitting here, this is the bullseye, this is the bullseye. If someone hits here, he will be more accurate. This is not accurate, but all of the shots that the person is hitting, they are in a close region. So he is precise but not accurate. Now for this third value that we have here is, this is both accurate because he is hitting near the bullseye, and precise because all of the measurements, all of the hitting of the arrows are at the same place. So this is not accurate because it's not even hitting the bullseye, neither the values are like a particular distance or like a fixed distance from this. They are not being consistent in the hitting also. This is not accurate, not precise, this is not accurate, but this is precise, this is accurate and precise. This is what the difference between the accuracy and precision is. Now let's move to the new concept called significant figures. Now The significant figures in a measurement, they include all the digits that are known plus one last digit that is estimated. I will show this to you through an example. Suppose this is a balance, this is the needle, this is 15, this is 16, 17, this is 14. This is a measuring balance. It measures, suppose you can put it like it is measuring the weight of something. Some weight has been put up. This is the meter that is showing the meter readings. Now if you can see it here, the value of this meter, now this meter shows 14 kg, 15 kg, 16 kg, 17 kg, everything is in kg. Now these values, if you see, they are in the integer values. So what I can say 15 is when the needle points at 15. Now if you see from here, this is somewhere in between 15 and 16. Now according to the machine that I have been given, I cannot tell precisely the value. What is the value? What is the value of, what is the mass of the, what can I say? Suppose I read it, I will say that this is 15.5 kg. So when you read it, you may say no, I find it a bit more inclined towards 16, it is 15.6 kg. Someone else says 15.4 kg. This is why, so if you can see here, what is the varying reason? Only this is varying. We are sure this is 15, this is more than 15. So this part is, we are confident of this 15. What is varying is this part. Now this significant figure, if you see, it includes all the digits that are known, all of the digits that are known. What are known is 15 is known, plus one last digit that is estimated. Now this is the last digit that you are estimating. Someone is telling 5, someone is telling 6, someone may say 4. So this is what the uncertain digit is. So the total certain digits, if you have to write it like this, total certain digits that you know for sure plus one uncertain digit. This gives us the number of the significant figures in a value that has been given from a measurement. So here if you see, what is the number of significant figures? It is 3, because these two are known. This is the third figure, because I have to take one uncertain digit. But suppose someone says it like this, 15.52. Will this be counted? No, I cannot count this. This is you have to take the first uncertain digit. This is the first uncertain digit. You don't have to go, these digits will all be uncertain, but you don't have to go to all of these digits. Only the first uncertain digit after the certain digits. So count the number of certain digits, then add to it 1, which is actually the uncertain digit. Now we know centimeters and millimeters. We have seen a ruler. If you see this ruler, you can see it here that this is 1 centimeter, right? And this distance, this is 1 mm. So now the measurement that you can make is something like, someone can measure 41.2 centimeter, someone can measure 41.3 centimeter. This is what the measurement can be done. These are given here. This is the measurement that this ruler can easily measure. It has been marked with these accuracy, this level of significant digits it can measure from this ruler. But what if something like your measurement comes like this, if it is in between? What will be this value? Now if someone has to write, 2 persons are using the ruler, one person will write this is 42.43 and someone else will write this is 42.44 centimeter. Now we know 42.4 is certain, up to this value we are certain. We are not certain of this value 3. So someone is saying 3, someone is saying 4, someone may say 5, 6, 7, whatever. So we have to calculate the number of certain digits that we are sure is 3 digits and then add to it one uncertain digit. This all the time we have to add 1. So find out the number of certain digits, add to it plus 1. Those. So here the number of significant figures will be 4. Now how will we find the number of significant figures when the number has been given to you? Now if the decimal is present, we have to start counting from the left. Like suppose you have 5.62. Here I have a decimal. So start counting from left. You have to count from left. 2, 6, 5. So how many significant digits? There are 3. Now why I am telling you to count from left is because, sorry, okay, I made the mistake. This is telling you to count from the left. So you have to count from here. This is 5.62. So you take the first, second and third, you have 3 significant digits. Now why we have to measure from the left is because suppose something is written like this, then we don't have to count these digits. Continuous zeros are not counted in the significant figures. That is the reason we have to count from here. Now when the decimal is absent, so it's like 1, 2, 3, 4, 0, 5. Start counting from the right. You have to start counting from the right. So this is 1, 2, 3, 4, 5, 6. These are 6 significant digits. Why from the right? It's because something is written like this. You don't have to count these 2 zeros. If you start counting from here, you will count these 2 also. So when we are measuring for non-decimal numbers, what you have to take is, you have to measure from the right, count the number of digits. Don't count the zeros that come before any that come after any non-zero digits. That means if you have this 0, 0, 1, then you have to count it. But if these zeros, they come before a non-zero, they are counted. But if they don't come before a non-zero digit, they are not counted. This is 1, 0, 0. You have to count this 3 again, because now there is one before this. But you don't count it if it's written like this. Okay. Now moving ahead, zeros encountered before a non-zero digit do not count. Zeros that are encountered before a non-zero digit, they do not count. This is what we are talking here. Non-zero digit, if you see it here. Now what are the zeros that are encountered before a non-zero digit? Here you have to measure from this. Now this is the non-zero digit. This is 0. Now that will encounter before a non-zero. So if there is a non-zero here, then you have to count it. But if there is no non-zero digit, you don't have to count it. Same case for here. If you have a non-zero digit here, you have to count it. But if there is no preceding non-zero digit, you don't have to count this. Okay. Now how many significant figures are here? In 100, if you can see, there are 3 significant figures. We can straight away tell there are 3. Now this is 10302.00. Now will you count it or not? Since we have to calculate this from left, 1, 2, 3, 4, 5, we don't have to calculate this because there is no non-zero digit here. So this is actually 5. What for this? What are the number of significant digits in this case? Now as we can see, this is a decimal place, decimal value, number with a decimal. You have to go from here. But since all these zeros are encountered, there is no non-zero digit here. So you don't have to count these. This is valid for both before and after that we are talking. You don't have to count this, only 1 is the significant digit. So number of significant digits are 1. Now if you see, these zeros are in between. So they come in counting of the significant figure. So they are 5. Now if you see here, these are 4. But we don't take into account for the significant figure the power of the values. So the number of significant figure here is again 3 to 5. Zeros are in between, so we count them. Now how to calculate when we are adding the significant figures? Like suppose I give you to add 2.339 plus 6.45. Suppose I have given you these 2 values and you have to add this, and after addition you will give me some value and you will tell me that, well, this is up to this places they are significant figure. We don't write the values ahead of the significant figures. We only write the values up to the significant figures, because the values after that are actually the uncertain digits, and in the significant figures we have already taken one uncertain digit, so we don't take all those uncertain values. So we write only in the terms of the number of significant digits that we have. Now if you look at this, I have given you example here. This is 2.33 centimeter, this is 3.0 centimeter. What you have to do is, you have to express the result with the same number of decimal places as the number in operation with the least decimal places. Means First what you have to do is put the decimal in same line, write the words, write the numbers sorry that are given to you, 2.33, 3.0, add them, symbol will be like this, add them. Now you have to look for the least decimal places in these two numbers. What are the least decimal places? As you can see, there are these 3.0 centimeter. So the result is rounded to 1 decimal places. Now you may wonder why I have taken this 0 as a significant digit. So there is an exception here. If something is given regarding a measurement, if something is given this centimeter, if something is given this meter, this kg, in that case we take this value for the measurement in the significant figure. So this you have to keep in mind. This is a star mark thing, that if something has been measured and given to you the value, if someone suppose simply says 3.0, the number of significant digits is only 1, but if she says 3.0 centimeter, he has done the measurement, then you have to take into account this significant figures. Okay. So suppose you have this 2.339 plus 6.45, how will we add it? We will write like this, this is decimal, this is 645, we add it 9, 8, 7, 8. Now the number of significant figures are less in this, that is 2 only, so this will become 8.79. Why we are writing 9 is because we have to round it off. Now since we have to write only in the number of significant digits, significant figures we have to take into account. So when we are writing, we cannot make it a value that is wrong, so we have to round it off. This we have done in our classes, lower classes also. We have to round it off to this places. There you are being told round it off to this many places. Here what you have to do is, here you have to take the call by yourself. You have to see how many significant figures are, and then you have to put the rounded value. So suppose for the sake of argument this had only two significant figures, then this value would have been written as 8.8. Okay. Now let's move to the next, that's how to calculate the significant figures in multiplication and division. Now in multiplication and division, what we do is that we do the normal multiplication that we know, and then again we follow the same rule. The same number of significant figures as are present in the number with the least number of significant figures. The two numbers that are given to you, you have to see which of them has least number of significant figures. Now as we can see, this is centimeter, so these are two significant figures. So we multiply it, we get 6.4, and the result is rounded. We have to round it. We are rounding when we know the number of significant figures, because if this is 6.4, if it has to be rounded to 1, if the number of significant digits is 1, then this value will become 6. Suppose this was 6.42 and the number of significant digits were 3, then you have to leave it at 6.42, because now this has 3 significant digits. Okay. So in this part we have studied how the measurements in the physical quantities are done, what are their precision, accuracy, how much a data is more relevant, how precise it is. We dealt with all of those things in this part. So for the rest of the part on the units and measurements, that will begin in the next class. Stay tuned for more videos. Thank you.